All right, last recording you guys have to listen to. This one covers two sections, so it is a little bit longer. It's over 5.2 and 5.3. And make sure again you have the guided notes and you will need a calculator. Okay, so we're going to start with 5.2, which is over compound events. All right, so the first thing we're going to go over is independent events. So two events are independent if the occurrence or the non-occurrence of one does not change the probability the other will occur. Okay, so one does not affect the other one. So for example, if we were draw a blue marble or roll a 2 on a die. Okay, so whether we draw a blue marble does not affect whether we roll a 2 on a dice. Okay, so these two would be independent events. If two events are independent, then the probability of A and B is equal to the probability of A times the probability of B. Okay, so only if the events are independent, then we get to multiply the two probabilities together. All right, so first example, we draw one card from a standard deck and we roll a die. Okay, these two are independent because it does not matter what card we draw from a deck, it will not affect the dice or the number we roll in the die. So these are independent events, so we know we're going to multiply. So we want to know the probability you draw a diamond and roll a 5. So we're going to have the probability of a diamond and a 5. So since they are independent, it's going to be the probability of a diamond times the probability of a 5. Okay, so let's just look at the probability of a diamond first. So remember, probability is want over total. So we're going to have a fraction. Here we're working with a deck of cards. So our denominator is the total. So if it's a deck of cards, we know we have 52 cards total. And then there are 13 diamonds in a deck. So I have 13 out of 52 times the probability I roll 5. Since we're rolling a dice, there are 6 options on a dice. We can roll 1 through 6, so my total is 6. I want a 5. There's only one 5 on a dice, so my numerator is 1. So if I multiply these two together, my probability would be 1 out of 24. Okay. So down here, probability we draw a red jack and roll an even number. So probability red jack and an even number. You can abbreviate, that's fine. So since they're independent again, because drawing a red jack will not change if I roll an even number or not, so I'm going to multiply the two. So probability of a red jack times probability that it's an even number. So if I start with the red jack, again we're in a standard deck of cards, so my total is 52. Okay, so we're looking for jacks. Remember there are 4 jacks in a deck, but we want it to be red. There's only 2 suits that are red, so I only have 2 options there. So I have 2 out of 52 for a red jack. And over here, we're rolling an even number on a die. So there are 6 options on a die. So that'd be my total. For an even number, I can roll a 2, 4, 6. So I have 3 options to roll. So 3 out of 6 will be my probability of an even number. Okay, multiply those two together. You should get 1 out of 52, or you can leave it as a decimal for either one. Doesn't matter. Okay, so that's independent events. If one does not affect the other, then you multiply the two properties together. Okay. So dependent events, the occurrence of one will change the likelihood of the next event. Okay, so independent, they don't change each other. Dependent, they do change each other. So think of they depend on each other. Okay, so for example, anything that says without replacement. So without replacement means they're going to be dependent events. Okay, because think of if we have 5 red and 5 blue marbles, and we draw one and we draw, let's just say we draw red. So if we had 5 blue and 5 red marbles in a bag, we had 10 total. Okay. If I drew 1 red, now I have 5 blue and 4 red, so now I have 9 total if I don't replace that red. Okay, so for my second draw, my total number of outcomes changed since I did not replace that marble. So this, or not replacing this, changes this total number for the second one. Okay, this is called conditional probability. Okay, and the formula for this, the probability of A and B is equal to the probability of A times the probability of B, and then we're going to draw a little line and then put A. Okay, and this right here, probability of B with the line A, this means probability of B given A occurred. And we're going to do an example, so it should make more sense in 1 second. But up here, I had 5 red, I drew one, I didn't replace it, so now I had 4 red and my total changed to 9. So A occurred, so now my total would be 9 for this one here. Okay. Or we can do it as probability of B times probability of A given B. Okay. Either formula is fine. Okay, so for example, we want the probability of drawing 2 aces from a deck of 52 cards if the first card is not replaced before the second is drawn. So since it says it's not replaced, we automatically know that they are dependent events. So we want the probability of an ace on the first and ace on the second. Okay, since it wasn't replaced, we said that they were dependent. So this means we're going to have the probability of an ace on first times probability of ace on second given an ace on the first. Okay, I'm just using this formula up here. So we have probability of A and B is probability of A times B given A. So my event A is like an ace on the first. So we have probability of A, which is probability of an ace on the first, times, now we have probability of B given A. My B is an ace on the second. So probability of an ace on the second given there is an ace on the first. Okay, so let's ignore the given part for now. If we look at an ace on the first, where we have a deck of cards, so we know our total is 52. If we are drawing an ace, we want an ace. There's only 4 aces in a deck, so that probability is 4 out of 52. Okay, so now we have times the second probability. So let's look at our denominator first. We had 52 cards to begin with. We drew a card and we did not replace it. So now we only have 51 cards left. Okay, so we want an ace, but we drew an ace on the first. So originally we had 4 aces to begin with. So let's say there's my 4 aces. I drew an ace on the first and I didn't put it back. So now I only have 3 aces left to choose from. So my second probability would be 3 out of 51. Okay, so multiply those together. That should be your probability, or you can write it as a decimal. Okay, so remember, without replacement, your denominator is going to change because we drew a card from the 52 and we kept it, so now we only have 51 left. We had 4 aces, but we drew this 1 ace and we kept it, so now we only have 3 left to choose from. Okay, go to the back to the chart example. Okay, so this chart here, they have results of a test of 200 patients. Okay, and we're going to find the probabilities of A through F down here. There is an example, or there is a problem like this on your test, so make sure you pay attention to this example. Okay, so let's look at the first one. We have the probability that it's positive given the condition is present. Anytime you see a given, you're not going to use the whole total for the chart. So this right here is the chart total. This 130 is the condition present total. The 70 is condition absent. Positive would be 120. Negative would be 80. Those are the different totals. This one is for the entire chart. Okay, so down here we have positive given that it's present. Okay, so we know we're going to have a fraction. We are given that the condition is present. So anytime you're given something, this is your new total. So we're going to ignore the chart total. So condition present, the total for that would be 130. So that will be my denominator. So anytime you are given a given, whatever is after the given is your new denominator or your new total. For my numerator, I'm looking for positive. So under the condition is present, the only ones that are positive is 110. So my probability would be 110 out of 130. Okay, again, every time you're given a given, that is your total. So we are given that it is present. So if we come up here, present is this column right here. The total is 130. Okay, so since I'm in this column, now I want to know how many are positive in this column. So in this column, 110 are positive, so that would be my numerator. Okay, we're going to do a couple more. So probability that it's negative given that it's present. Okay, again, we're given the condition is present. So if we go to condition present, we're looking in this column here. Since that's what we're given, that's our total. So the total for present is 130. And we're going to stay in this column. The number that is negative would be 20. So 20 out of 130. Okay, so down here, negative, given that it is absent. So we're given absent. So we're going to look at this column here to see what our new total is. So here's the column of absent. The total is 70. And in this column, the only ones that are negative are 60. And so down here, positive, given that it's absent. So again, we're given it's absent, so we're looking here. The total for absent is 70. And the total positive under that is 10. Okay, and the last two, if you look at these, condition is present and positive, present and negative. These don't have any givens, so these all had a given, so that gave us our total. These two don't have a given, so that means we're going to use the chart total. Okay, so anytime you have a given, that is your total. So whatever you're given tells you your total or your denominator. If you have no given, then you use the chart total. Okay, so given, our totals are different. Down here, there's no given, so we're going to use the chart. So I'm just going to go ahead and fill in my denominators for both of these. So if we look down here, the chart total is 200, so both of them are going to have a denominator of 200. Okay, the first one, the condition is present and positive. So if I come to the chart, here's positive, here's present. So the only one that are present and positive is 110. So that probability would be 110 out of 200. Down here, present and negative. Come to the chart. Present, negative, go to where they meet. 20 of them are present and negative. So 20 out of 200 would be that probability. Okay, so just remember, anytime you are given a given, the given or the part after the given tells you your total or your denominator. Okay, so all of these you're given a given. Down here, there is no given, so you're using your chart total. Okay, go to the next page. Okay, so this one is over mutually exclusive events. Okay, if they are mutually exclusive, that means they share no events or no common outcomes. Okay, so an example of this would be roll an odd number or a 2. Okay, so we cannot roll an odd number and a 2 because 2 is even. So this means that they are mutually exclusive, so they have no common events. And this formula would be probability of A or B equals probability of A plus probability of B. Alright, so for example, we are given a bag of 11 marbles, or 11 blue, 5 red, and 3 green. Okay, so we know we're going to have to find the total, so that's just what I'm going to do first. So if I have 11, 5, and 3, that means I have 19 marbles total. So I want the probability that I draw a red or a green. Okay, these are mutually exclusive because I cannot draw a red and a green on the same die because marbles are on the same draw because a marble is only one color. So I can only draw a red or a green. So it has no common outcomes. So probability of red or green is equal to the probability of red plus the probability of green. So let's just look at the probability of a red marble. So we know our denominator is the total, which is 19. And there are 5 red marbles. So the probability of red is 5 out of 19. Okay, these do not affect each other, so their probabilities are just separate. So we just did red, so now let's ignore red and look at green. Okay, so we still have 19 marbles total. If we come up here, there's only 3 green, so 3 out of 19. And make sure you don't get it confused with the replacement ones. So the only time you change your denominators is if it says there was no replacement. These are 2 separate events. Okay. Add those together. we should get 8 out of 19 for the probability. Okay. So we have the probability that's red or blue. So again, they're mutually exclusive because they cannot happen together. We have one draw or one draw. We cannot draw a red and a blue because we're only drawing one marble. So if we look at probability of red, we know there's 19 marbles total and there are 5 reds. Probability of blue, there's 19 marbles total and there are 11 blue. So add those together. Probability would be 16 out of 19. Okay, so now if two events are not mutually exclusive. They are not mutually exclusive. This means they may share an outcome or a common outcome. Okay, if this is the case, then we have the probability of A or B is equal to probability of A plus the probability of B minus the probability of A and B. Okay, so it starts out the same, but then we just subtract the overlap. Okay, so we want to know the probability of rolling an even number or a number larger than 3. So we have probability that it's even or greater than 3. Okay, so down here I'm just going to list all the things that we can roll on a dice. So we can roll the numbers 1 through 6. Okay, so let's just look at the first event. We want an even number, so probability of an even number. So I'm just going to circle all the even numbers. So 2, 4, and 6. Okay, now I'm going to look at the numbers that are larger than 3. Number larger than 3, I'm going to box all those. Oops. So 4, 5, 6. These two were selected in both of them. So they are both even and they are both larger than 3. So that means that these are not mutually exclusive because two events can happen together. So I'm going to have the probability that it's even plus probability that it's greater than 3 minus the probability that it's even and greater than 3. Okay, so we know we're going to have all these fractions. And we know the denominator is the total, so if we look down here, we have 6 outcomes, so all of the denominators are going to be 6. So for each situation, we still have 3 outcomes to choose from. So let's start with the first one, probability that it's even. So if I come down here, I have 2, 4, and 6, so I have 3 even numbers. Probability that the number is greater than 3, 4, 5, and 6, so 3 options that are greater than 3. Probability that's even and greater than 3, 4, and 6, so only 2. Okay. So if I add and subtract, then I would get my probability would be 2/3. So sometimes if it's easier to list out all your outcomes, you can go ahead and do that. So again, these two are not mutually exclusive because right here we have even numbers that are greater than 3. So the events happened together or they had a common outcome. All right, go to the back. We have a couple word problems. Okay, so Andrew is 55 and the probability that he will be alive in 10 years is 0.72. Ellen is 35. Her probability is 0.92. Assuming the lifespan of one has no effect, I'm going to box this because that's going to be important, on the lifespan of the other, what is the probability that they will both be alive in 10 years? Okay, so we had 4 different situations. So if we go back to the 4 that we wrote down, independent, dependent, mutually exclusive, or not mutually exclusive. If one has no effect on the other, that means that these are independent events. Okay, because one is not changing the other. So I want the probability that they will both be alive in 10 years. So I want the probability that Andrew is alive and Ellen is alive. Okay, so go back to the formula that we wrote down. Probability of A and E, since they are independent, is probability of A times the probability of E. Okay, we know the probability of Andrew is 0.72, and then the probability of Ellen is 0.92. So if we multiply those together, 0.6624 would be the probability that they are both alive. Okay, so anytime you are going through and reading a word problem, look through the key terms. So I found no effect, so I can go through and see which one of the four it is. Okay. Okay, so a procedure for testing cameras consists of drawing 2 cameras at random from a lot of 100. So I'm going to stop here. So here's my 100. If the lot contains 100, we know that this is the total amount. And here's my key term, without replacement. Remember, without replacement, go back to the 4 we wrote down. This means that they are dependent events. Okay, so if both are defective, then the lot is rejected. Find the probability that both cameras are defective if the lot contains 10 defective cameras. Okay, so I want the probability of camera 1 being defective and camera 2 being defective. Okay, just because I'm drawing 2 cameras, and we want to know that the lot, or that it is defective if both of them are defective. So camera 1 is defective and camera 2 is defective. So since they are dependent, I'm going to have probability that camera 1 is defective times probability that camera 2 is defective given camera 1 is defective. Okay, so that's just the formula that we wrote down. Okay, so let's ignore this second part right here. So we want the probability that camera 1 is defective. So we know that the total was 100, so there are 100 cameras total, and only 10 of them are defective. So if I want one of them to be defective, I have 10 that I can get out of the 100. Okay, so remember, since it's dependent or without replacement, my denominator is going to go down. So I already drew a camera. So now I had 100 cameras, I drew 1, so now I only have 99 cameras left in the lot. There were 10 defective cameras, I already drew 1, so now I only have 9 left to choose from. And multiply those together, get 1 out of 110. I remember, without replacement, we have to do this given or conditional probability. So after I do the first probability, I had 100 cameras, I drew 1, so now I'm down to 99. I had 10 defective, I drew a defective, so now I'm down to 9 defective. Okay. 2 more word problems. Okay, so we buy a pair of slacks in a regular waist size without trying them on. The probability that the waist is too tight is 0.3. Probability that it's too loose is 0.1. Okay, so let's just find this probability, or total probability, for now. Probability that it is too tight or too loose. Okay, these two events cannot happen together. It cannot be too tight and too loose, so we can just add them together. So we know the probability that it's too tight is 0.3. Probability that it's too loose is 0.1. So probability that it's too tight or too loose is 0.4. Okay, this problem doesn't really specify, but we're just going to say that the length of the slacks already fit. So all we're looking at is the waist size. So this right here is the probability that it won't fit. If it's too tight or too loose, it's not going to fit, but we know the length is perfect. Okay, we want to know that the probability that the waist will fit. So if you go back to the 4 properties that I had you write down at the beginning, we know the probability that it will fit plus the probability that it will not fit is equal to 1. Because remember, there's only 2 outcomes or 2 scenarios here. So one or the other is going to happen, so we have 100% of both of them happening. So we want to know the probability that it's going to fit. We know the probability that it does not fit is 0.4, and that should be 1. So if we solve for the probability that it's going to fit, we have a 60% chance of it actually fitting. All right. Last word problem. So 80% of students need work in math, 70% in English, and 55% in both. So probably I think it'd be math or English. So right here they need work in both. This means that there's an overlap. So this tells us that it's not mutually exclusive. So since it's not mutually exclusive, we're going to use the probability of M plus probability of E minus probability of M and E. So we have to subtract the overlap. So we know the probability that they need help in math is 80%. Probability in English is 70%. Probability in math and English is 55%. Okay, so I'm just going to rewrite these as decimals so I can add and subtract them. Okay, so add and subtract, then we get 0.95 would be the probability. Okay, here's your homework assignment for section 5.2. Notes are continued on the handout that you have, so make sure you keep it. We're going to start with tree diagram for the 5.3 video, so make sure keep these notes with you, and then go ahead and write down your assignment.